Hi everyone, my name is Migyeong Gwak. I'm a PhD candidate in computer science at the University of California, Los Angeles. Today, I will talk about GAIToe, gait analysis utilizing an inertial measurement unit for toe walking detection and intervention. This is a collaborated research study with Children's Hospital of Orange County, CHOC, and funded by CHOC Foundation. Most children begin walking at 12 to 15 months of age. Often, in the early stage of walking, children try different foot positions for walking. Walking up on their toes may be part of this. As they grow up, they should walk with their feet flat on the ground and should walk with a heel-toe pattern. If walking up on their toes persists, this is called toe walking. Toe walking refers to walking pattern in which a child walks on the balls of their feet and there's no contact between the heels and the ground. If toe walking in a child who has been evaluated by their doctor and no medical reason has been identified, we call it idiopathic toe walking. Idiopathic toe walking, ITW, sometimes referred to as habitual or behavior, occurs when a child walks on the balls of their feet for an unknown reason. ITW happens in otherwise healthy and typically developing children, and some children are able to walk with their feet flat when asked to do so. The incidence of ITW has been estimated at 7 to 24% of the childhood population. Persistent toe walking may induce four deformities, ankle dorsiflexion limitations, poor alignment of posture, and impaired balance. Suggested treatment for ITW include observation, special training procedure, muscle stretching, orthotic therapy, supportive footwear therapy, serial casting, intramuscular Botox type A injection, and finally surgical heel cord lengthening. However, the necessity and effectiveness of this treatment are controversial. Several studies report that conservative treatment actually do not have any lasting effect on the toe walking, and even after surgical treatment, the failure rate is over 30%. There were several approaches to track human locomotion and walking status by embedding multiple wearable sensors in the shoe or insole. However, their complicated system and algorithms are not designed specifically for toe walking detection and interventions. More promising analysis and interventions of ITW still needed to be developed and validated. A real-time assessment system enables real-time intervention. Because ITW is a habitual or behavior activity among healthy children, behavior change techniques may motivate them to put their heels down. Based on control theory, designing a system to record walking activities to compare the daily number of toe strikes and heel strikes can bring positive outcomes to the individuals with ITW. We introduce a remote toe walking monitoring system, GAIToe. It uses a single IMU and an insole to detect physical activities such as toe walking, heel-toe walking, standing on toe, normal standing, sitting on toe, and normal sitting. The sensor unit is located underneath the hindfoot and includes all the circuitry. The connected Android application collects data from the sensor unit and achieves minimal user interaction and intuitive visualization. When the app is branched, it automatically starts to scan and connect to the BLE module using the pre-stored MAC address. A chart on the screen displays the number of toe steps in red bars and the number of heel-toe steps in green bars. The previous 6 days of step counts are shown on the first 6 bars, while the real-time step counts are shown on the rightmost bar. The app saves the collected data into the cloud-based database every 5 minutes. Our hardware implementation goal was to maximize the utilization of currently available and affordable devices in order to reduce the expense of our custom-designed system. With all this consideration, storage soles with a container space at the bottom satisfied our need to house the shoe sensor unit and to insert it into any running shoes. Storage soles are made with flexible polyurethane foam, so they are waterproof and easily trimmed for nearly any shoe size. We designed and 3D printed a case and lead using PLE material to house the circuitry component. Adafruit Feeder Development Board has an ARM Cortex M0 processor with up to 48 MHz operating frequency and 256 kilobyte flash memory. It also provides BLE wireless protocol. We connected an 800 milliamp hour lithium polymer rechargeable battery as the power supply of the board. GAIToe is equipped with an MPU 9250 motion tracking device, which is a multi-chip module consisting of 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer. It captures shoe acceleration, angular velocity, and magnetic north. A mini vibration motor is connected to Adafruit feeder board to provide real-time biofeedback. It provides 2 types of vibration, a short vibration for 3, 6, or 9 consecutive toe contacts, and a long vibration for 10 consecutive toe contacts on the ground. The long vibration can be turned off with any heel strike. This biofeedback protocol is defined in consultation with orthopedic and physical therapy experts. The power efficiency of the system is tested by emulating a worst-case usage scenario, which is a continuous toe sitting including a series of vibration with a transmission rate at 20 Hz. In our experiment, the battery almost consistently discharged the voltage and stayed at the minimum voltage of 3.5 volt for 30 minutes. Then the battery increased the voltage up to 3.6 volt before it cut off. We figured out that the system lasts 30.75 hours under continuous operation, which is more than enough for daily activities. Wearable IMU signals are sensitive to small movement, and the activities cannot be determined by a simple threshold-based algorithm. So we decided to train a machine learning classification model. We first collected activity data from 14 healthy subjects. They were instructed to have 200 strides of heel-toe walking and toe walking, as well as 2 minutes of sitting and standing. We extracted features from the IMU data such as magnitude, and tilt angles of 3-axis signals, and the roll and pitch angles from the acceleration data. We divided each signal into windows of 10 data points and calculated the mean and standard deviation of each window as features. We selected an extra trace classifier from scikit-learn, which had the highest cross-validation result among other classifiers. This chart demonstrates the cross-validation score achieved from examining these estimators and the maximum depth of the extra trees. Considering the limited flash memory space on the Arduino compatible microcontroller, the best 10-fold cross-validation with 88% accuracy was achieved by setting the estimator to 25 and maximum depth to 8. We ran tree-based feature selection to remove the irrelevant features from our classification model. The most significant features were acceleration pitch and tilt angle mean, gyroscope magnitude mean, and standard deviation of gyroscope roll signal values. As you can see, the precision recall F1 score of each label, the normal, sit, and stand label has the highest precision and lowest recall. However, toe walk label holds the lowest precision and highest recall. All 4 classes have roughly the same F1 score. Furthermore, the leave one subject out cross-validation of the trained model was 86%. If activity is determined as normal or toe walking with the classification model, then the steps counting procedure takes place. Regarding the gait cycle, the forefoot is off the ground during the swing phase, which happens once for each step. We found that non-consecutive peaks of magnitude of gyroscope signal is in a window with 10 samples were an accurate estimation of step counts. The signal retaining a higher value than the window average is classified as peaks of the window. For example of step counting, as shown in sequence of 2 windows, the consecutive peaks at index 5, 6, 7 considered as only one step. If the last signal in the previous window and the first signal of the current window are both higher than the mean signal values of each window, the first signal of the current window is not perceived as a step. In order to achieve the objective of providing a real-time intervention, we concentrated on developing the activity recognition algorithm on the microcontroller. 10 healthy adults between the ages of 21 and 44 volunteered to try our GAIToe in their running shoes for the preliminary system evaluation. They attempt 6 sessions, including 100 strides of toe walking, 100 strides of heel toe walking, 2-minute toe standing, 2-minute normal standing, 2-minute toe sitting, and 2-minute normal sitting. We instructed the participant to perform these activities correctly, then supervise them in order to obtain clear data. Subjects were asked to walk at a comfortable pace on a level ground. During this experiment, there was no incorrectly detected toe step during heel-toe walking among all subjects. However, within 100 toe steps of some subjects, about 2 to 9 steps were incorrectly detected as normal steps. The average accuracy of heel-toe step counts were 93%, while accuracy of toe steps count were 84%. To evaluate our vibration protocol performance, we asked the subject to record the short and long vibration while walked for 100 toe steps. The number of expected short and long vibrations are presented in the last two rows of this table. The mean absolute error for toe step detection was 15.9. The MAE was 0.7 for short vibration and 0.3 for long vibration. GAIToe is a remote monitoring system for activity recognition and improving walking patterns of individuals with habitual toe walking. It provides a wearable, portable, non-invasive, energy-efficient, easy-to-use, and low-cost platform for pervasively monitoring walking patterns in daily life. Our sensor unit, utilizing an IMU, is designed to be inserted into any running shoe. The proposed activity recognition algorithm is developed to identify different activities and give real-time biofeedback. This year, we have recruited children with ITW through the Children's Hospital of Orange County. We asked the subject to run our Android app in the background and wear the waist bag with the smartphone while they're trying our shoes. They were responsible for charging the system every day, and we just finished data collection to examine our system's robustness and durability with the repeated usage. We're planning to do further analysis on the collected data. We can identify IMU-based gait parameters and validate effectiveness of gait behavior changes for ITW children. GAIToe may enable orthopedic experts and researchers to investigate the detailed gait parameters and foot movement. It may become an assistive tool to develop a more effective intervention technique. Again, my name is Migyeong Gwak from UCLA, and I'll be happy to receive any questions or suggestions about my presentation.